Okay, picking this guy up. I had to end the video quickly because I can only do the videos for 15 minutes. Otherwise, YouTube won't let me upload it. And I don't want to go to the effort of figuring out how to do longer YouTube videos. So we stick to 15 minutes. So there's my explanation for the abrupt end of the video. I have no explanations why it took me so long to graph that. I was just not being a good teacher. So if you do teacher evaluations, you can rank me a few points lower for stumbling through that. But now you know that I'm not perfect. So just recapping what we were doing on this problem, we were supposed to graph this guy. So there's my basic shape. We moved that point around 1, 0. So there was that point. Move it left 2, 1, 2, up 5, there's that point. Then moving this asymptote right here, moving it left 2, 1, 2, there's my new asymptote, there's my graph. So this new asymptote here, 1, 2, this new asymptote is at x equal -2. So now answering all the stuff that they wanted, the domain, left to right. So it's almost at -2, so -2. Then it goes to the right forever, so -2 infinity. Range is low to high. It's going down forever and very slowly up forever, but still up forever. So the range is -infinity to infinity. And then my vertical asymptote, x equal -2. And there's that problem. Okay, moving on a little bit. Previously, it was stated you can never find the logarithm of a negative number or 0 using real numbers. And again, a little bit of a disclaimer here. You can't find the logarithm of 0 for anything. Logarithm of 0 is just always undefined. Negative numbers, if I let you use complex numbers, there are things you could do there. But we're not going to use complex numbers here. This idea that I can't find the logarithm of a negative number or 0 is that concept of domain, the numbers you can put into your calculator. For example, clear this. And we'll just use a common log. If I do log of -2, error, non-real answer, it won't do that. Let's quit that. If I ask it to do log of 0, yep, error domain, it won't do that. And if I do the same thing, natural log of -8, error, non-real answer. If I try to do natural log of 0, again, it's not going to do it. We can only do logarithms of positive, strictly positive values, and that's domain. See right there, domain. Domain are the numbers that you can plug into the function and come up with an answer. I wasn't able to plug in any of those answers, any of those numbers into my logarithm functions and get answers. Domain are the numbers you can successfully plug in. So this refers to domain. In general, the domain of a logarithm is the set of numbers that will result in a strictly positive argument. In general, the domain of a logarithm is the set of numbers that will result in a strictly positive argument. To find the domain of a logarithmic function, set the argument greater than 0 and solve. And again, we're talking about really very basic logarithmic functions, nothing much more complicated than this. I could do some bizarre stuff and maybe have it be different, but very basic stuff here. So find the domain. So we're going to do right where it says there. Set the argument greater than 0 and solve. So 14. Take that argument, set it strictly greater than 0, and solve. So that's mean -2x is greater than -14. And then really why we want to do this problem, one of the reasons we really want to do this problem, get that x alone, divide both sides by -2. And again, I would look at the class and say, what do we got to do here? We just divided an inequality by a negative number. And about 80% of the class would remind me to flip that inequality. And so we got x less than 7. And so my domain would be -infinity to 7 in integral notation. If they wanted the set builder notation, that'd be the set of all x such that x is less than 7. If it's a test that I'm grading, that's a good enough answer there. If it's some sort of computer thing, the computer's probably going to want one of those two things. But strictly less than, so it has to be a parenthesis. Nothing special about this one. It doesn't matter if it's log base 6, natural log base e. You take that argument, set that argument greater than 0, and solve. So that's 3x greater than 18. Divide both sides by positive 3, so no need to flip that inequality. X greater than negative 6. So negative 6 to infinity, or the set of all x such that x is greater than negative 6. And there are those guys. So the key thing is to remember this part right here. Set the argument greater than 0 and solve. That when that's, at this level, when we ask for the domain of a logarithmic function, we're just asking you to do that. So just memorize that. Okay, so previously we graphed log base 2 of x. And in the previous section, we graphed 2 to the x. And so they're both graphs. So over here, this guy on this side here, this is f of x equal 2 to the x, and over here this is g of x equal log base 2 of x. And then let's dash in one more line. Let's dash in this line right here. And that's the line y equals x. And notice that if I was to take my paper and fold it across the line y equals x, those two graphs would lie on top of each other. That concept is reflection, that those two graphs reflect across the line y equal x. Well, one thing we learned long ago in section 2.7 was that when graphs reflect across the line y equal, let me rephrase that. What we learned in 2.6 was that inverse functions had that property. That they had the property that when you graphed a function and its inverse, that those graphs would reflect across the line y equals x. Those reflect across the line y equals x, so that would imply that 2 to the x and log base 2 of x are inverses of each other. It doesn't prove it, but it implies it. And we're just going to then accept this as a fact. They are inverses of each other. 2 to the x and log base 2 of x are inverses. And then in general, fact. For f of x equal log base e of x, then f inverse of x is b to the x. Or y equal log base b of x and y equal b to the x are inverse of each other. And so there is an important concept. That logarithmic functions and exponential functions with the same base are inverses of each other. Logarithmic functions and exponential functions with the same base are inverses of each other. Then if we try again, think all the way back to section 2.7, the mathematical way of saying that was that their compositions went back to x. That f of f inverse and f inverse of f gave x. That they undid each other. That if you did both of the functions, compose both the functions together, you always got back x. So that gives us two more logarithmic properties. That log base b of b to the x equals x, and specifically if we talk about common logs, then log of 10 to the x equals x. And if we talk about natural logs, natural log of e to the x equals x. And then the second property, b raised to log base b of x equals x. Specifically, log raised to log x, or 10 raised to log x is x, and e raised to the natural log of x is x. That because they are inverses, inverses undo each other. That's what inverses do. Because a logarithm and an exponential with the same base, because they're inverses, they undo each other. You can say, I don't particularly like the word, but I'll use it, and I'll use it a lot, even though I don't like it. They cancel. So here's a logarithm, base b, an exponential of a base b. We're doing both of them. We're composing them. One is inside the other. Because they're inverses, they have to cancel or undo each other, giving us just x. Same thing here. Here's an exponential, base b. A logarithm, base b. They are composed. One is inside the other. Because they're inverses, they have to cancel or undo each other, and we get x. So as long as you have this matching bases, log base b of x, of b to the x, b raised to log base b of x, when I have those matching bases, because they're inverses, they will, quote unquote, cancel. Then specifically, natural log of e to the x is x, and e raised to the natural log of x is x, because remember, the base of the natural log is e. So you do have the matching bases here. And these will creep up quite a bit, which is why I said those first. But then the same thing is going on here. Remember, if a base is not written, it's understood to be 10. Log base 10 of 10 to the x. The bases are matching. Logarithms and exponentials, same base or inverses, so I get x. Same thing here. Base is 10. Base is 10. Matching bases, we get x. So evaluate each of the following without a calculator. And so the point here is just to observe that matching business. First of all, rewrite with exponents. Logarithms go with exponents. So rewrite it. We'll try to rewrite it a little neater than that. So log base 6 of 6 to the 1/2. Once I have this matching business, because logarithms and exponentials with the same base are inverses, we get 1/2. Same thing over here, and I'll be very explicit. Natural log is base e. So I got logarithm base e, exponential base e. I have that matching. Logarithms and exponentials with the same base are inverses, so they cancel, leaving me 7x. Same thing here, and again, I'll be really specific. Natural logs are base e. So again, I have those matching bases. When I have those matching bases, because exponentials and logarithms are inverses, they undo each other or cancel. And so I get 3 to the x to the 4th. Same thing over here. So that's log base 10, or that's 10 raised to the log base 10 of 34. Again, matching. They cancel, and I get 34. Have a horrible, horrible page break here. That's supposed to be on the next page. But it is what it is. Same thing here. Base not written. Base is understood to be 10. So got that matching thing going on again. So 5. And the same thing on the last one. Base is 7. Base is 7. Matching bases. They cancel. And so I just get 4x. And we'll end this video here, and we'll do this word problem on the next page. Horrible, horrible page break, but that's life. We'll end this video here and then do this last problem in the next video.